some people, those who have again rejoined. Shall we start? Okay, good. Good morning to all of you. I will just start discussing. Okay, I want to, as I told you, I want to rush up whatever I have covered in the last class. Once again, I would like to revise. Okay, actually, already I told you the behavior of any physical process can more often be described in mathematical form, especially in a differential equation form. Okay, the behavior of any physical process, right? In this first unit of your mechanics of materials, that is the problem. See, the permission is asked. Okay, in mechanics of material subject, what is the thing? Actually, the first unit, differential equation. Okay, differential equation of the deflection curve. Okay, a beam is bending due to the load acting on it. Okay, for example, we will consider a cantilever beam, right? A cantilever beam is there, which is subject to a point load at the free end. P, either P or W, you can use it. Okay, here I usually P in the discussion. Okay, let us see. Subject to a point load P at the free end, right? Here the beam deflects like this. Actually, we are considering two adjacent cross sections which are dx apart, right? At the section at M1 at M2, right? Let O be the center of curvature, rho radius of curvature, theta angle of rotation. Okay, so if you draw a radial line at the point M1 and M2, okay, the radial means normals at the point normal to the curve at the point M1 and M2, they meet at O. Okay, so the radius of curvature is termed as rho here. So the angle subtended at the center is d theta. Okay, so I am just given the magnified view of this portion. This is two adjacent section here, M1 and M2, these points. Okay, this portion of the beam, deflected portion of this beam, I have drawn for visualization purpose this much. As I told you already, this beam will not, in actual practice, the beam will not deflect this much. The deflection will be minute. Okay, just for visualization purpose, I drawn magnified manner like this much deflection we are showing for visualization purpose. Okay, so the two sections are at dx apart. Okay, the vertical deflection of relative deflection of M2 when compared with the M1 is dy in the vertical direction. Okay, so the deflection of the beam from its initial position, the deflection of point M1 from its initial position is y. That's why it is right. Yeah, right. So this is I told you y plus dy. Okay, the angle of rotation at point M1 is theta. How do you draw it? You have to draw a tangent at M1. Okay, the angle made by this tangent with the horizontal is theta, right? Here the angle of rotation at M2 is theta plus d theta, some incremental angle, obviously. Okay, you draw a tangent at M2. The angle made by this tangent with the horizontal is the angle of rotation here, which is theta plus d theta. Likewise, I have given all this thing here. Okay, from the figure we can understand what is rho into d theta. Angle subtended here is d theta. So radius of curvature into d theta gives you the arc length here, ds. Okay, that's what we have written here. Rho into theta equal to ds. Therefore, rho equal to ds by d theta. Okay, so what is curvature? This curvature is nothing but 1 by radius of curvature. Okay, so curvature is equal to 1 by rho, which is equal to d theta by ds here. This is equation 1. And also the slope tan theta. Okay, the slope tan theta is equal to dy by dx. Why dy by dx? Actually, I told you for visualization purpose we have drawn this much, but in actual practice the deflection will be very minute. The beam will be almost flat. That's why you can treat it as a right angle triangle here. This portion can be treated as a right angle triangle here. That's why this tan theta is equal to opposite side divided by adjacent side. Okay, dy by dx. Tan theta is equal to dy by dx. That's the equation 2. That relation also we can get. That I have written here. Most beams undergo only very small rotations when they are loaded. Hence, their deflection curves are very flat with extremely small curvatures. Hence, we can make some approximations. Okay, already told you, we engineers do a lot of approximation and we make a lot of assumptions, and thus we may do approximations although we do approximation, our approximated values are acceptable. Okay, we make some assumption based on that. We approximate our solution. Although our solutions are approximated, they are acceptable level. We do the solution. Okay, they are acceptable. Okay, that's what I told you already. So from this figure again, right angle triangle, if you see cos theta equal to adjacent side divided by hypotenuse dx by ds. Okay, and that's what I have done here. Therefore, ds equal to dx by cos theta. Likewise, also we can get it. Okay, since cos theta is approximately equal to 1 when theta is small, we obtain ds is nothing but dx. Okay, actually, I told you the angle of rotation is very minute because the beam almost flat. In actual practice, it will not deflect much. That is why this we are getting this kind of approximation. This ds approximately is equal to dx. Therefore, the curvature of this equation 1 is can be rewritten as curvature 1 by rho equal to d theta by, instead of ds, you can put dx. Okay, that is equation 3. Also, since tan theta is approximately equal to theta when theta is small quantity, we also can say tan theta equal to dy by dx. Slope, already I told you, theta equal to dy by dx. That is, the slope is nothing but the angle of rotation at any point on the beam. The slope of the beam at any point is the angle of rotation. Okay, at that point in the beam, right? Also, since tan theta approximately is theta, when theta is a small quantity, we can approximate equation 2 as follows. Okay, thus for small rotation of a beam, the angle of rotation and the slope are equal, right? Note that the angle of rotation is measured in radians, right? Taking derivatives of theta with respect to x, we get. Okay, so here I told you theta equal to dy by dx. Just you take the derivative of theta, that is d theta by dx is equal to d square y by dx, right? So theta is the angle of rotation is equal to slope dy by dx. If I take derivative of angle of rotation d theta by dx with respect to x, I am getting d square y by dx square. Therefore, equation 3 and 4 implies curvature 1 by rho is nothing but d theta by dx equal to d square y by dx square. Same thing. Okay, I have written here. Okay, so the curvature is d square y by dx square. Right. This equation relates the curvature to the deflection y of the beam. Already told you last class itself. I explained. Once again, we are refreshing or reviewing it. Okay, it is valid for a beam of any material, provided the rotations are small, right? If the material of the beam is linearly elastic and if it follows Hooke's law, the curvature, it is well established in the literature. Okay, this relationship already well established in the literature, that is curvature is equal to minus m by ei. Okay, but here we have got a curvature is equal to d square y by dx square. Therefore, in which m is the bending moment and ei is the flexural rigidity. Okay, ei is, please keep it in mind, ei is called a flexural rigidity, right? Equation 5 is valid for larger rotations as well as small rotations. Okay, so it's well established in the literature already. The curvature is equal to minus m by a. Therefore, you can equate this d theta by dx. Okay, the derivative of slope is equal to d square y by dx square is equal to minus m by a. From this, we are getting ei. Take ei here. Ei d square y by dx, so dx square is equal to minus m. So you should not forget this. You should remember the basic differential equation for deflection curve of a beam. The basic deflection equation for deflection curve of a beam, you should not forget. You have to remember. This is very, very important. I told you. A d square y by dx square is equal to minus m, which is the basic differential equation of the deflection curve of a beam. This equation can be integrated in a particular case to find the angle of rotation theta or the deflection y, provided the bending moment m is known. Okay, already I told you in the last class itself. I told you just once again revising it. Okay, so double integration technique. That's what. If you want to get a slope, you have to integrate this equation. If you want to get a deflection, you have to integrate once again. Okay, so that is why this method is called double integration method or double integration technique. Okay, a slightly modified form of it is called Macaulay's method of calculating slopes and deflection. That I will discuss it later. Now I want to do how to do this double integration technique for some simple problems. Okay, only a single load is acting. Suppose several discontinuous loads act, several point loads acts. We have to do it by Macaulay's method, which is nothing but this also double integration technique. Little bit some modification we do. That I will explain later while discussing this Macaulay's method with you. Okay. So I'm going to see some simple problems on cantilever beams. Okay, so cantilevers, we are considering cantilever beams. There is a cantilever beam subject to point load at the free end, W. You can take it as capital P or W, whatever you want. Okay, right. The book which I referred was Mechanics and Materials by Timoshenko and Gear. So he has used W, so the same thing I have adopted in my notes, I think. So okay, capital W. The length of the beam is L. Consider a section at a distance x from the fixed end. Say the deflection, the vertical deflection at that section is y. Okay, the vertical deflection at the free end is y suffix b. Y suffix b means deflection at b. That's the meaning of it. Okay, we already established the EA d square y by dx square equal to minus m. Okay, dA d square y by dx square is equal to minus m. Okay, so what is the bending moment at this section? What is the bending moment at this section? Either you can investigate left side of the section or right side of the section. If you want to investigate left side of the section, it is required to determine support reaction here. Already I told you, in cantilever beam, you need not determine support reaction. Straight away, you can start investigating the free end portion of the beam. Okay, so this is the section under consideration, right? Investigate the right side of the section. Okay, what is the bending moment at this section? Okay, the bending moment due to this W. The W is acting vertically downward. Already I told you, bending moment due to all downward loads are negative because it produces hogging bending moment. Just you have to imagine you are fixing this beam here and applying load here. The beam tends to bend in the hogging manner, tension top, right? That's why negative bending moment produces negative moment. So the bending moment is minus W into this is the length. What is this length? Here it is from fixed end, this is L. From fixed end, this is X. So this length is L minus X. Okay, so minus W into L minus X is the bending moment. If substitute here, okay, some student latecomer has come admit. Okay, it's the disturbance. That's why I told you to join all of you through using PEC mail ID, right? So what did I say now? Yeah, so already we have minus M. Now minus W into L minus X become plus W into L minus X. Okay, so now I want to determine slope. Okay, what to do? If you want to determine slope, we have got a differential equation which describes the deflection curve of the beam. Okay, if I want to get a deflection at any point, I have to integrate this governing differential equation. Okay, called a mathematical model. Okay, so what to do? Integrating dA dy by dx is equal to just integrate W L into x because we are integrating with respect to x minus this is W into x, no, minus Wx square by 2 plus C1 integral constant. This already explained in the last class. That's why I am just rushing up. Right. At x is equal to now what to do? Now we have after integration we have got an equation in which there is a unknown parameter that integral constant is there. We have to evaluate it. Okay. How do you evaluate? We have to evaluate it by the known value points. Okay. By applying that is called a boundary condition. At boundaries, we know the values. Okay, at some boundary of the beam, we know the values of the deflection and slope. That's why it is called a boundary condition BC. You should not forget boundary condition BC. At the fixed end, all movements are restrained. The rotation of the beam as well as the translation of the beam, everything constrained. Okay, no degrees of freedom available. Everything constrained there. That's why the rotation, angular rotation is 0 here. That is slope is 0 here. As well as the deflection also 0 here. Okay, this is the equation for slope. That's why at A, otherwise when x is equal to, both are only the same. Either I say at A or at x is equal to 0 means at A, that's the meaning. At x is equal to 0, the slope is 0. dy by dx is equal to 0. If substitute this equation, dy by dx is 0, here it is 0. X is equal to 0, this becomes 0, this becomes 0. That implies the integral constant C1 equal to 0. We have evaluated. No integral constant exists, which becomes 0. Okay, therefore the equation is reduced to A dy by dx equal to WLX minus WX square by 2. Equation 1, slope equation. Integrating again, EY, okay, is equal to WL x square by 2 minus WX cube by 3 into 2, 6, okay, plus C2, another integral constant. After sign integration we have done. That's why it is called double integration method. 2 times we are doing integration. That's why it is called double integration method. So we have got the integral constant C2. We have to evaluate it from the known values. That is using boundary condition. We have to apply boundary condition. So if you apply boundary condition, you can write here, apply boundary condition, apply BC. If you put apply B dot C, boundary condition, that's the meaning of it. At A, that is at A means what? At x is equal to 0. The deflection is 0. We know the value of deflection at a fixed end, which is 0. Okay. At x is equal to 0, y equal to 0, which implies C2 equal to 0. If you substitute x equal to 0 and y equal to 0 here, C2 becomes 0. Okay. So we have evaluated the integral constant, which is found to be 0. Right. Therefore, the deflection equation is given by EY equal to WLX square divided by 2 minus WSQ by 6. This only. Okay. This only. See, because C2 becomes 0. That's why I have written this. This is equation 2. This is a deflection equation, right? This is called a deflection equation. Now, using this deflection equation, slope equation, we can determine the deflection at any point on along the length of the beam. The deflection or the slope at any point along the length of the beam, we can determine. Okay, we are interested at the free end of the beam, the deflection is maximum. It is obvious. Okay, and also the angle of rotation. In other words, the slope also maximum at the free end. Okay, we are interested. We are so curious to know those values. That's why what I am doing, the maximum values we are in which we are interested. So at x is equal to L, that is at the B means what? At the free end of the cantilever B means the value of x is L there, no? That's why at x is equal to L, theta suffix B, that is angle of rotation at B. The slope, angle of rotation is the other thing, but slope at B, theta B is equal to dy by dx at B, that is slope at B is equal to 1 by EI. Slope equation is here. So it becomes 1 by EI into this. In this, you have to substitute x is equal to L. So you substitute x equal to L, WL square minus WL square by 2. So you are getting WL square by 2 EI. I already told you, you should not forget. Whenever in many competitive exams, such a questions you will be getting. Okay, wherever people ask you, see, there is a kind of beam substituted to point load at the free end. The point load is, say, capital P at the free end. What is the slope at the free end? They ask immediately how to say PL square by 2 EI. Okay, they say use rotation W, WL square by 2I. They use rotation capital P, PL square by 2A. You have to tell immediately. Okay, similarly, the deflection at the free end, y suffix B is equal to 1 by EI into this one. Okay, y equal to 1 by EI. Into in this substitute, x is equal to L in this equation. So you are getting WLQ by 3EI, right? So this you should not forget. Somebody will ask you, let's say, can you beam substitute to point load free P at the free end. So what is the this one? What is the deflection at the free end? If somebody asks you, immediately you have to tell them, tell him it is PLQ by 3EI. The deflection at the free end will be PLQ by 3EI. You should tell immediately. You should not forget. You are civil engineers. Lifelong you should remember. Because when you apply for a job, you have to appear again an entrance exam. Many objective type exams, this kind of questions are being asked. So I advise you to remember these values. Okay. Next, we are considering. Now I am coming to this today's class discussion. Okay. So let's say cantilever beam subjected to UDL. Okay. W of intensity W per unit run, per unit length or per unit run. Intensity W. Okay. Subject to UDL, cantilever beam. Consider. I have drawn the deflection profile. Okay. For visualization purpose, I have drawn this much. But in actual practice, we are seeing all the beams. No. Is there any visible deflection in it? No. They are very minute. Okay. For visualization purpose, I have drawn this much, right? Here. Now, what is the deflection, rotation at the free end? Say the deflection at the free end is y suffix B. And rotation means you have to draw tangent to this curve at this point. And the angle made by this tangent with horizontal is theta suffix B. That is the rotation at a slope at B. Rotation or slope, both are on the same, I already told you. The slope at B, deflection at B, okay, at free end. Right? Now we will discuss. We know EI d square y by dx square equal to minus m. You have to write here. We know EI d square y by dx square is equal to minus m. Okay. So consider a section XX. Okay. At a distance x from the fixed end. Now, what is the bending moment at this section? What is the general expression for bending moment at this section? I want to investigate free end portion, right side of the section. Okay, free end portion of the cantilever. I already told you. So, what is the intensity of UDL here? It is W into this length. What is this length? Which is L minus X. Okay, from fixed end, the length of the beam is L. From the fixed end, the section is at a distance X. That is why the remaining part of the length of the beam is L minus X. Okay. So W into L minus X is the intensity of the load into perpendicular distance from the section to the at the center of run of this UDL. Center of run of this UDL is L minus X divided by 2. That's why the bending moment is minus W into L minus X into L minus X divided by 2. That is minus W L minus X whole square divided by 2. Okay. Already the minus sign is there, though it becomes plus because it produces hogging bending moment here. Okay, but bending moment due to all downward loads are negative. Already I told you, it produces hogging bending moment. That is why it is negative bending moment here. It becomes plus like this. So I am expanding it. W by 2 into A minus B whole square. A square plus B square minus 2AB. Okay, because W divided by 2 I have taken outside here. So A minus B whole square I am just expanded here, right? Very good. So integrating A dy by dx is equal to W by 2 into integrated this one with respect to x, L square into x plus x cube by 3 minus 2L is a constant, 2L into x square by 2, integration is over, plus integral constant C1. Now we have to evaluate this integral constant using boundary conditions. Boundary conditions means what? Known values, okay? Known values of slope and known values of deflection at certain salient points, certain at support, especially at support, at salient points, right? At x is equal to 0. At x is equal to 0 means at fixed end, at A, okay, at A, at fixed end. At x is equal to 0, the slope dy by dx equal to 0, we know. If you apply this in this equation, substitute dy by dx equal to 0 and x
ஹலோ சாருங்கடா ஓனரு
இல்ல தெரியல காண போயிடுறா
ரெக்கார்ட தம்பி பார்த்து பேசு.
நமக்கு போன மாதிரி அவருக்கு வெளில போயிடுச்சு போல சாருக்கு. ஏன்டா
இப்படிதான் இருக்கும்னு நினைக்கிறேன்.
நம்ம வெளில போல சாருக்கு நம்ம வெளில வந்துடும். நமக்கு கால் அவருக்கு சார் கால் வந்துருக்குன்னு நினைக்கிறேன் நான்.
டேட்டா கால் ஆயிடுச்சு, ரீசார்ஜ் பண்ண போயிருப்பாரு.
ஏன் கொரோனா வந்து
ராகுல் சார்
என்னடா சைலண்ட்?
என்ன சொல்றாரு
ரஞ்சிதா?
தேவா
பகல்தாகர வந்து பார்க்க விட மாட்டா.
ஆமா ஆமா சார் வந்துட்டாருன்னு நினைக்கிறேன்டா.
சரி 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 ஆஃப் பண்ற.
Sir, not audible. Please put on your mic.
Now audible? Am I audible to all of you?
Yes, sir.
Yes, sir.
No, I don't know. Actually, it disconnect automatically. I don't know why. Boys?
Sir,
Hello,
call
boys?
வந்தா டிஸ்கனெக்ட் ஆயிடும் சார்.
என்னம்மா கால் வந்தாவா?
கால்
இல்ல எனக்கு போன்ல மெசேஜ் வந்தது, வாட்ஸ்அப் வந்தது.
சார் எனக்கும் டிஸ்கனெக்ட் ஆயி தான் சார் உள்ள வந்துட்டு இருக்கு.
என்ன ப்ராப்ளம்?
அது ஏன்னு தெரியல சார்.
அது சில டைம் அப்படிதான் சார் வருமே.
இல்ல எனக்கு வந்து வாட்ஸ்அப் கால் வந்தது, வாட்ஸ்அப் லோட் ஆச்சு, டிஸ்கனெக்ட் ஆயிடுது. ஓகே, நான் சொன்னேன் அதாவது ஜூம்ல we are comfortable சொன்னா கேட்க மாட்டேங்கிறாங்க காலேஜ்ல. ஓகே, I will proceed. Thank you. I will proceed. But screen is visible, no? Few minutes.
Yes, sir.
Few minutes, just. Okay, only mail is visible to you. Right. Yeah, now this notes is visible. Right. Few minutes more. Is it okay? Now the notes is visible to you. Right. Now can you able to see the notes? No. Can you able to see the notes?
Yes, sir.
Yeah, very good. I will proceed. Right. So where I stopped here. Okay, we have evaluated the integral constant as C1 equal to 0. Therefore, EI dy by dx square is equal to this expression, which is called equation 1, slope equation. Okay, slope equation. Next, integrating again, EI y is equal to differential equation. EI y is equal to w by 2 into L square into integrate this one, x square by 2 plus, if you integrate this, L power 4 divided by 4 into 3, 12 minus here, what is that? 2L. We have 2L, no, this is 2 actually, it's not rubbed, 2L. 2L into x cube by 3. Here 2 is there already, so 6. Why is this rubbed? I don't know. 2 here also 2 is there, right? Plus C2. At x is equal to 0, now you apply the boundary condition. We know at fixed end the differential is 0. Okay. At x is equal to 0, if you face any problem, you tell me. In case you are not able to listen my audio or something, you tell me. At x is equal to 0, the diffraction at fixed end is 0, y equal to 0. Therefore, the integral constant C2 becomes 0, which implies C2 is equal to 0. Therefore, EIY is equal to W by 2 into L square, right? X square by 2, this one. Okay. So, because this becomes 0, C2 becomes 0, only this expression that I have written here, right? Which is called deflection equation. Now, we are interested in determining the value, because in this cantilever beam, the angle of rotation as well as the deflections are maximum at the free end. We are interested in determining these values at free end. Okay. So, what I am doing, just at x is equal to L, that is at free end, the value of x is L. At x is equal to L, okay, that means at free end, at B, that's the meaning of it. Slope theta suffix B is equal to dy by dx, that is angle of rotation at B is equal to, which is nothing but slope, dy by dx at B is equal to 1 by A into W by 2 into this one. Substitute x is equal to L in this expression. Substitute x is equal to L in this expression, you substitute. So, if you substitute, you will be getting WL cube divided by 6EI. Please remember, W, small w, it's not capital W, small w, because it's UDL. Small w L cube divided by 6EI. You should not forget. A cantilever beam subjected to UDL. What is the slope at the free end? It is WL square, WL cube divided by 6. 3 clear, twice, 6EI. Right? Next, deflection at free ended. YB is equal to 1 by EI into W by 2 into this one. This expression substitute, x is equal to L. Okay, so you will be getting, after simplification, taking okay, LCM, you will be getting this one, W L power 4 divided by 8 EI, right? Please remember, just see this. You substitute x is equal to L in this expression in order to determine deflection at the free end at the support B, not support, at point B, at free end, YB is equal to the deflection at the free end is equal to this much. Okay, you should not forget this. Let's say cantilever beam subject to UDL. What is the deflection at the free end? If somebody asks you, you have to say WL power 4 divided by 88. The slope is WL cube divided by 6EA. You have to tell. These values you should remember, right? Next, we are considering another cantilever beam in which a point load is acting, which is not acting at the free end, somewhere on the length of the beam. Okay, at a distance L1 from the fixed end it is acting, right? How to determine slope, maximum slope and maximum deflection at the free end? That we are going to see now. Please consider, please listen. We are investigating a cantilever beam in which a point load is acting somewhere along its length. Okay, say at a distance L1 from fixed end, right? Now the length of the beam is L. I am interested in determining the deflection of the free end. Okay, now the deflected profile of the beam I have drawn like this. Here it is curved because bending is there, bending movement is there. That's why the beam bends up to this point, up to the point load point. Thereafter, no load is acting here. Okay, since no load is acting, here the bending moment is 0. Between CB, there is no bending moment exists. It's 0. That's why this part of the beam is a straight line here. Okay, that we will discuss it later. Okay, so whatever angle of rotation is there, you draw a tangent at point C. The tangent nothing but this straight line here. Okay, the tangent at C is nothing but the straight line portion of this beam here. Right. So the angle made by this tangent with the horizontal is theta C. That is slope at C. Here slope at B is equal to slope at C. Same thing, because the beam not bends further, because there is no bending movement exists here. That is why there is no tendency of bending. The beam is just a straight line here. That's why whatever slope is there, same slope also there here. Theta B equal to theta C here. Okay, that's what I have written here. But the deflection is more here, YB. Here YC. Okay, deflection at the point C, deflection at point B. So likewise, I have shown all the values, required values at the feature points. Okay, I have given here. Now I will write mx is equal to what is the bending moment at the section XX, which is equal to W into, from this you can write L, what is the distance between section and W, L1 minus X. Okay, from here it is X distance, section is at X distance, that's why L1 minus X. Okay, so mx equal to minus, it is a hogging bending moment, that's why minus W into L1 minus X. Okay, with this I will finish today's lecture, don't worry. EI d square y by dx square. Oh, timing also wrongly shown. Why 9:31 AM only shows few minutes more? That is why I am facing a lot of problem the recording and all. Some problem is there. Better I would avoid using this laptop. Some problem is there with the battery of this laptop, I think, in the power connection. Okay, better I will avoid using it in the next class. I will use some other laptop. Okay. Since it's not times are shown wrongly, it may not record, it will stop, it will come out, it will do all these things because of that problem. Okay, right. Is it visible? Oh, yeah, I'm sorry for the intervention. Okay, sorry for the disturbance. Actually, is it audible to all of you? Yeah, audible.
Yes, sir.
I'm sorry for all these things today, because we are learning this platform. No, it's okay. What did I say? This one. Yeah, here. EA integrating. We are integrating this. EA dy by dx is equal to W into L1x. Just to expand W into L1, so W L1x, W into x, so Wx square by 2 plus integral constant C1. So we have to integrate as usual. If you do it at x is equal to 0, dy by dx is equal to 0, slope is 0 at fixed end. Therefore, the integral constant becomes 0, which implies C1 equal to 0. Therefore, this deflection equation, slope equation is CA dy by dx equal to WL1x, this one, same thing. It is 100% similar to that of first problem. The only difference is, instead of L, we have L1 here. Integrating again, EAY is equal to WL1x square by 2 minus WX cube by 6 plus C2. Apply boundary condition. At x is equal to 0, the slope deflection is 0. At fixed end deflection is 0. Therefore, which implies the integral constant is 0 there. Therefore, EAY is equal to WL1 x square by 2, this one. Okay, no C2 here. So this is equation 2. This is differential equation This is the equation 1, slope equation. Okay. Now we are interested in determining the deflection and slope at point C, at point load point. Okay, salient point, feature point, and then at free end where its values are maximum. We are interested in the values at free end also. Let us see first. First, at x is equal to L1, substitute theta c. Slope at c is equal to, that is rotation, angular rotation at c is equal to, this is nothing but du by dx at c. Slope at c equal to 1 by EI into this one. So we are getting WL1 square by 2A. Already you know. Cantilever beam subject to point load at the free end. The rotation is W L square by 2EI. Here, when the point load acts somewhere L1 distance from fixed end, the rotation at that point is WL1 square by 2EI. That's all. Okay. So the differential at C is equal to 1 by EI into WL1 cubed by 2. Substitute x is equal to L1. Okay. In the above expression, this expression. So you will be getting WL1 cube by 3A. Already we know. Cantilever beam subject to point load at the free end. The differential at the free end is WL cube by 3A. We know that. When the point load acts somewhere L1 distance from fixed end, the value is WL1 cube by 3A. Okay. So the rotation as well as the deflection at the point load are known to us. Okay. As there is no load in portion BC here, in this portion BC, CB, okay. As there is no load in the portion BC, there is no bending moment anywhere in BC. Therefore, deflection curve will be a straight line between C and B. Okay, that's how I told you, right? So the slope of theta B is equal to theta C, already explained. Slope theta B is equal to theta C here, okay? Because this beam is a straight line portion here. Because the no bending moment here, so the beam will not bend further. It will just like a straight line here. Okay, it will be straight there. That is why we can determine deflection YB is equal to YC. So the deflection YB here is equal to YC plus, what is that? Plus L minus L1 into theta C. What is that? Arc length. So here the deflection YB is equal to YC plus this is what is that? Theta C into L minus L1. The remaining length here is L minus L1. That into theta C. You will getting approximately arc length, just straight line here. Okay. That does this way we have to determine. Approximated, everything approximated, no. YB equal to YC plus L minus L1 into theta C, arc length. Mari. Just please try to understand. This length is L minus L1. Okay, into theta C. The angular rotation here will give you the further deflection here. That's why YB is equal to YC plus L minus L1 into theta C. Okay, that's what I written here. So you substitute, you will be getting some expression, this kind of expression like this. This way we can determine the deflection at the free end. If any numerical values are given, you have to compute this way. Please remember, if any numerical values are given, you have to compute this way, right? Shall we proceed? Shall I proceed or sufficient today? Okay, it's a simple case you will see. I will finish up the cantilever beams today. Please listen to me, because thereafter simply supported beams comes. Only few more discussion, only 5 minutes discussion. Now you consider another cantilever beam subject to a couple at a free end. Okay, clockwise couple. A clockwise couple M at a free end is acting. The length of the cantilever is L. At a distance X, consider a section. What is the bending moment at the section? Mx is equal to minus M. Why? It's a clockwise moment. Anti-clockwise positive for us. Clockwise is negative. In other words, just you visualize, you imagine, you put your hand in that point where I am putting, I have put my cursor. Just you rotate it in clockwise direction. What happens? The beam tends to bend in a hogging manner, tension top. The beam tends to bend in a hogging manner, tension top. That's why it's a negative bending moment. Okay. So the Mx equal to minus M, right? So therefore, EA d square y by d square is equal to minus of minus M, which is plus M. Okay. Therefore, EI, I am integrating. EI dy by dx equal to M into X. It's not M suffix X. It is M into X. Please remember. Because M is there. If you integrate with respect to X, M into X plus C1. Okay, I am evaluating the integral constant. At x is equal to 0, dy by dx is equal to 0, which implies C1 equal to 0. Therefore, EI dy by dx equal to m into x. It's not m suffix x, it is m into x. Equation 1. Okay. Next, you integrate again. EI y is equal to mx square by 2 plus C2. Okay. Now I am applying the boundary condition. At x is equal to 0, at fixed end, y equal to 0. Therefore, which implies C2 is 0. The integral constant is 0. Therefore, EI y equal to mx square by 2. Okay. Signed equation. Now, I have got the slope equation and deflection equation like this after evaluating the integral constants. Okay. So now, I am interested in determining the slope and the deflection at the free end of the beam. Right. So, at x is equal to L, that is at the free end of the beam, theta b, the diagonal rotation at b, which is nothing but slope at b, dy by dx at b is equal to, substitute, right? 1 by EA into m into L. Instead of x, you substitute L. So, ml by EA. Similarly, the deflection YB equal to ml square divided by 2 EA. This also you should not forget. Please remember, you have a cantilever beam subject to a couple at the free end, a clockwise couple at the free end. Okay. Is it clockwise or anti-clockwise? Clockwise means downward deflection. Anti-clockwise means upward deflection. That is the only difference. Okay. A cantilever beam subject to a couple at the free end. If the couple act in clockwise at free end, the beam deflects downward. If the couple act anti-clockwise at free end, the beam will deflect upward. That is the only difference. Okay. But the values are the same. What is the rotation? ml by EA. What is the deflection? ml square by 2a. You should not forget. Okay. So a cantilever beam subjected to a couple at the free end. What is the, somebody asks you, what's the deflection at the free end? Immediately you have to say ml square by 2a is the deflection. ml by EA is the rotation at the free end. Okay. These values you have to remember. That is why this method is called a double integration method, double integration technique. Okay. Today I finished the cantilever beam. Simple cases, elementary level cases we have taken. Okay. Still I have not discussed with you Macaulay's method. Macaulay's method na, in a beam if several discontinuous loads act, discontinuous UDL or discontinuous point loads, several point loads act. How to deal? How to do this problem? How to apply this double integration techniques there? Okay, some modification is there, some simple procedure is there. That is called Macaulay's method. It's also a double integration method. Some procedure we are going to follow there. Some technique. Okay, I'm stopping. Why are you telling? I already told you. No, with this I will stop. You have to listen. I'm actually okay. Already told you. I know that with this I will finish. But it is my duty to give you explanation because I am dealing with the average student. Okay, so I have to tell again and again. No, any other go. Right? So with this I will stop. Okay, today class is over. Okay, bye. Bye all of you. Today class is over. Bye. Okay, you leave one by one. You can leave one by one. Totally, how many of you are attending class today? Yeah, today as usual 61. Can any one of you note down the attendance? I don't know, but they told me it is being recorded. How it is being recorded, I don't know. Let us see. Later we will go through the video and I cannot. I don't want to disturb you. Otherwise, I will ask someone to note down the attendance. Because it's showing the list here, no? Someone should, because you should have to listen. Okay, I will stop first this recording, right? I will stop the recording now. Stop recording. Very good. I have recorded.